in most languages, a variable has a value all the time, right? If it hasn't been initialized, it has a random value. But if you try to print it, in general, it will print, right? Some languages, such as Java, will not compile if they don't not detect that the variable has been initialized correctly. But in general, all variables will have a value. In Prolog, however, and in constraints, so this is an extension of the paradigm, Prolog's paradigm, a variable doesn't necessarily have a value. It may be unbound, right? The downside of that is that whenever it takes a value, it keeps the value forever, sort of, right? So, it is relatively easy to see why this is important, because the type of the computation is monotonic, right? You keep adding information to the system. But in general, you can express a relationship between variables without a value for those variables being computed immediately, right? So we've seen that if we load the library of finite domains, right, CLPFD, right, we can say x is assigned y plus 1, and the system is fine with that. Right, no variable has taken any value, right? And the system doesn't get upset. It simply says, well, there's nothing I can do with it right now, so let me put it somewhere in a place we call the constraint store. And as I accumulate more information, I'm going to see whether I can refine this or, derive more precise information about it. You might expect that, for instance, when you add more information in the form of maybe x is 3 minus y. This should lead to a unique solution, right? So this would be a system of linear equations that can be solved. I think it leads to we want integers. Let's get one that has integers. So I think 4 will give me integers, right? 4 minus y. So this will have y equals 1 and x equals 2, right? As solutions. So you might say, well, now the system should have enough information to derive a unique solution from there. But you see, the system actually doesn't do that, right? The reason for that is that there are different solving procedures embedded in CLP. We have loaded one of the weaker, well, it's not weaker, it's actually quite strong in certain respects, but it's not strong in the respect of solving linear equations, and there are other solvers. We'll see them very soon. Actually, let's just, I'm just not sure how, but we can give it a try. In the previous class, I finished explaining this, and then I moved on to linear constraints. So I can take the previous system of equations, and if I put them within curly braces, and I use the regular equality, I don't get anything. Undefined procedure. Not CLPFD. What am I saying? CLPR. Okay, so this is the library, and oh, I get 2.5 and 1.5. So it's not a good one. Was 3 better? Yes, 3 was better. So you see, this one does solve linear equations. However, it doesn't solve them in integers. It might seem to you easier to solve equations for integers than real numbers, but that's not true. Real numbers are a lot easier than integers. What do we do with the first one? Let's see if the first one still works. Yes, still works, and we want actually to have a 3 here, right? So what we can do is try to generate, at this point, combinations of values that may be tested against the equations. So we start, first of all, by specifying intervals, domains for these variables. We take an educated guess and say, well, x and y cannot be larger than 10 and smaller than minus 10. So let's say that x is in minus 10, 10, and y is in minus 10, and 10. All right? So you can see now that the system has been able to derive a bit more precise information. So that was our expectation. But the system says, well, you see, when x is minus 10, y cannot be larger than 9. Sorry, when x is 10, y cannot be larger than 9, right? From here. So we're going to derive a limit for y at 9. And when x is minus 10 here, y cannot be lower than minus 7. So we're deriving a limit of minus 7 here. Similarly, when y is minus 10 here, is that? So when y is minus 10, no, wait, yeah, so the largest value of y is 9. So when y is 9 here, right, x cannot be lower than minus 6. Right? Is this clear? So using the information that is given, the system always tries to shrink the domains of the variables until hopefully they become singletons, at which point we have discovered a solution. What do we do if we still haven't discovered a solution? Well, there's a very simple solution, as a matter of fact. We have a predicate labeled, if you remember. In the other constraint solver, it is called labeling. There are some syntactic differences, and I'm taking the solutions that I'm going to present today from a module that I have been doing last year, and I've been using the other constraint solver, so we're going to dabble a little bit in the other one. But let's stick with what we know for the time being and wonder what is there to do if we are at this point where we still haven't a unique solution and we want to continue the search. Well, if we look at x equals in minus 6 and 10, right, that can be rewritten as x is minus 6 or x is in minus 5 and 10, right? So I can write x in this way. We can create a choice point. What isn't it like? I think it's too many special symbols. Okay. So the system derives more precise information. So now you see the following: that when x is this precise value, right, it can be clearly verified that there's no solution for it, right? So the system says, oh, well, I'm left with this guy, and this is what you see here, that x is minus 5 to something. But because of this information, because of this refinement, right, minus 5 contributes to y being 8, and y being 8 contributes to the limit of x being 9. So it has been reduced. So every time we provide more information, actually the system is aggressive in deriving even more information for us. All right? So what can we do next? We're here. We know that the domain is between minus 5 and 9. What does the system do? So we're trying now to simulate what label would be doing. Well, x is minus 5 to 9. So we can say x is minus 5, or x has the domain minus 4 to 9, right? Right? So again, we get minus 5 will not produce a solution, right? It's clear. So we're left with minus 4 to something, but the upper limit again has shrunk here. The shrinkage of the upper limit will lead to a shrinkage in the upper limit of y. All right, and we know for sure now that the domain is even smaller. And you see, in fact, we do not have to go through all the pairs of values for x and y. We started with a domain of minus 10 to 10 for x, minus 10 to 10 for y. That's 11 values for each. And you might potentially think that we have to try 21 to the power of 2, which is 400 and something pairs of values, right? But it's nothing like that, because every time we perform this split of a domain, right, the system will perform a shrink that is even more aggressive. So in the end, we're going to go to the point where we actually do not have to pick any value for y. Y will be completely determined by the value of x. So the interesting aspect is how many such splits. You see, you can see each of these splits as a level in a search tree. We can think of, let me go here, right? So I'm going to do, for x, I'm going to split, sorry. So I'm going to try to, my pen is completely damaged, unfortunately. I have this pen tablet, right? So here I'm going to have, what choice did we make first? First choice was -6 and 5 to 10, right? So x is assigned, or -6 is given the value, is bound to the value. That's the correct terminology. And x in -5 to 10, we said initially, right? And this one fails, and we go here, and we have 2 more branches. So one branch will have x equals -5, and then we're going to move. But now we know that x, when it was -5 to 10, actually it was not -5 to 10, it was -5 to 9. So this choice is actually -5 to 9. So we say now x is -5. And here we are left with x in -4 to 9. And we keep going, and the question is, how many levels are we going to go? Right? You might foresee, we might think that it's 21 to the power of 2. Right? But we actually are going to do a lot fewer. So let's try another one. X is -4 or x in -3 to 9. Right? So again, shrinkage, -3 to 7, -4 to 6. So definitely this one didn't work, because if it did work, we would have a unique solution, because the value a unique value for x entails a unique value for y. Right? But that unique value for x did not verify either of the constraints, so then it didn't work. So we're left with -3 to 7. So we can say x hash -3 or x in -2, 7, right? -2 to 6. So we get the x hash equals -2 or x hash equal -1 to 6. Right? So now the shrinkage is smaller and smaller. We don't get that much, but we still get a shrinkage of 1, so that's progress if you want. I would like to cut and paste that, but there's the command line doesn't allow me. -2 or x in -1 to -5, right? And we could actually split the interval into halves. That's potentially more effective, right? -1 or x in 0 we didn't have any shrinkage in x, so 5, we didn't have any shrinkage in x, so 0 to 4 and so on, right? X not equal, yes, x equals 0 or x in 1, 4, And we still haven't gotten to the correct solution. And we won't have to get to a unique value. You'll see that. 1 or x in 2, 3. So now we should get this, the exact solution already. Yes. All right. So clearly x is assigned 1. Is x, I guess the value 1 is not a solution, right? Because if it were a solution, can you make that stop? Get a hammer and... Where is it coming from? Oh, I see. Yeah, throw it out of the window or something. So clearly this is not a solution because otherwise you would see x equals 1 here, right? You can't say that x equals 1 here and then get a solution x equals 2. All right? So this is the split that we have. Either x is equal to 1 or x is in 2, 3. You see, we haven't reached to a point of specifying a unique value. But that unique value is derived by the system automatically. All right? And why is it derived by the system automatically? Because once we figure out that we have to be between 2 and 3, right, when x is equal to 3, y is outside its domain, right? So y, you see last time, was between 0 and 2. So if x is equal to 3, y so if x is equal to 3, so this equation would give me that y can be at most 2, which is fine. This equation can give me that y is at least 0, which is still fine. If when x is equal to 2, that's the solution, right? So how come?
You don't want to x equals 1. If x is not 1, then y cannot be 0. So x cannot be 3.
No, but this is, they're completely independent. There's a stream of computation that goes on the x equals 1 and find out that that's not a solution. Then x equals not 1 has been undone, and all you have is x is between 2 and 3, right? So when x is between 2 and 3, all you have is this. You're working on this stuff, right? So you're working on this stuff, and x is between 2 and 3.
I think y
so
0 is out.
So x is 3 gives you y equals 0, which is correct, is in the domain. X equals 3 here gives you y equals 2. So this is still...
Different value for y. In the first equation,
no, so all you do in constraint propagation is bounds. You're checking the limits of the interval. What it doesn't happen at this point is checking separately both values and decided that one of the values is not a solution. At this point, you're going to try the following. You're going to say, well, x is at most 3 here. X is at most 3 here, right? Does this entail that x has to be greater than 0?
Because x at least 2, right? So y is at least 1.
X at least 2.
Y is at least 1, right?
So y is at least 1, which means that 0 cannot be in the domain. Okay, correct. So x is at least 2, which means that y is at least 1, which means that 0 cannot be in the domain, right? So y is at least 1 when I go here. When I go here, it means that x cannot be 3. So then 3 is removed from the domain, right? And it remains that x equals 2. So in many cases, we do not have to propose to test. We do not have to test the x equals 2 specifically, right? The fact that we have these inequalities based on the domains will lead, and the fact that the variables are integers will lead necessarily to a unique solution. Okay? And in the end, we didn't do 400 tests. We did much less. All right? So this is what we need to take from here. One, it is possible to specify relations between variables instead of specifying computations that assign values to variables. Right? Whenever we specify a relation that for which we do not have enough information, we simply delay it. We put in a constraint store, right, with the hope that later we derive more information to work on it and derive more information will be accumulated, and that will allow derivation of more precise information from the previously delayed constraints, right? So how does that happen? Every time I add new constraint, I have to go back and retest or reprocess the old constraints and see what new information I'm getting from them. What is the information that we're pursuing when we do this? Most typically, if we work on integer constraints, as is the case here, we are pursuing limits. So we are settling for what are the limits, upper and lower bounds for every variable. And with every new information, right, we see whether we can recompute the limits. We make one pass through all the delayed constraints, and maybe at some point in some variables we derive new limits, we shrink the domain. And that shrunken domain, when we go again through the entire list of constraints, may shrink other domains. And we have to do this iteration through all the constraints, right, until we go an entire round without making any changes. And that's, we know we squeezed out everything we can squeeze. Okay? So you can, in principle, figure out that this computation might be not so efficient, right? But it is extremely expressive. I'm not telling the system how to solve the problem. I'm telling the system what problem to solve, and the system solves it, figures out a way to solve it for me, right? I can be a stupid programmer. I can afford to be a stupid programmer in this with this paradigm. This is called declarative programming. The concept appeared in the 70s when it was hoped that, artificial intelligence is going to be so good that you're going to have this interaction with the computer where you just say in English what you want to compute, and the computer will figure out the best and fastest way to do it. So that dream has not quite come true, though artificial intelligence has progressed by leaps and bounds, but not quite there yet. And this is the best you can get so far, right? So in terms of programming language, we're discussing the perspective of programming language. We're not discussing the perspective of efficiency. The domain of constraints. So we separate here two things, right? One is the language aspect, which means we are embedding a constraint language inside a general purpose language, which is Prolog. And the other is the aspect of solving problems, procedural problem. And you can see that we can see a bit of that as well, because we have to select different constraint solvers to work for us. And in that area, there has been a lot more progress. So there are a lot better solvers called SMT solvers that are a lot more general and are not generally used in the context of logic programming, of program. But this is one of the best examples of marriages between two paradigms, constraint programming and logic programming. They mix together very well. They created a new language called constraint logic programming, which is what you see here. And the power is sort of apparent because you're saying this, and you don't have to know how to solve this. Okay, and you can do it in many cases. We have seen one where the solution was much faster because of the particular type of equations that we're having. Where was that? Somewhere above. We used linear constraints, so this is even simpler, right? But our constraints will not always be linear. We don't always have that luxury, and our constraints will not always be solvable in real numbers. Sometimes we want specifically integers, which make things quite a bit complicated. Is this clear? So it is an example of embedding one language inside another. There are other examples. For instance, SQL is regularly embedded in C, just that the way of embedding it in C is not by creating a new language. It's just you take an SQL command, you make it into a C string, quoted, and you have a procedure that sends that string to a database server, right? So C as a language is not modified. Even though when you look at the new program that you have written, you have to intermix the semantics of SQL with the semantics of C to understand what that program is doing. So as a programmer, you're inside a different paradigm, even though syntactically you have not created a new language. Here we have created a completely new language, right? But, well, to a certain extent, because you can say, well, I mean, in Prolog we can define operators as we please, right? That's one thing that we have seen. And the library that we have just loaded defines those operators as it pleases. Those are user-defined operators. They don't come from the compiler or anything, right? The entire CLPFD library is written in Prolog. It's not written in C or anything. The Prolog compiler has not been changed in any way to accommodate constraints, all right? So in a way, you can say, well, this is still Prolog with just one library. But it looks like a new language. It looks like it has its own operators. All right, so I'm going to switch to the other compiler, where I'm going to solve the same problem. So what would we say normally? We of course don't want to do this every single time, like write this long sequence of disjunctions, right? So normally we would say label xy, and that performs the entire string of disjunctions that you have just seen automatically, right? So, of course, it gets a lot simpler in this way. Eclipse Prolog works a bit differently, right? So first of all, it has a command line exactly similar to SWI, but comes with this top-level GUI, which I don't find it very nice, but that's why I prefer to use SWI Prolog for level 2, because the interaction is more natural. It's more Pythonish. Here we input the goal here, and we see the interaction in this window, right? So the goal goes in one text field, and the interaction goes in a different right text field right here, and the output and error messages will go here, right? It's not all in one place. So I'm gonna load the library, and of course the library is called different, has a different name and different command. So library of IC interval constraints I'm going to use here. Lib IC. All right, and then I'm going to take this and I'm going to change it to fit the new syntax. So the predicates have the same name, hash equal, right? However, the in becomes double colon, and we can use a list of variables here, so we don't have to put the two variables in separate declarations. And the predicate would be called labeling. Because why would people agree? Okay? And we get the same solution. So essentially that's the same thing. Now, interestingly, and if I go in as the AW Prolog, that's correct as well. I don't need to label both variables. Just labeling one is enough. Why? Because every distinct value of x will engender a unique value of y or no solution, right? I will never be in the case where one value of x will give me two possible values of y. If that was the case, then once I have fixed the value for x, I would have to label for the values of y as well. But that's never the case. So this would work equally well. So now you see that, you know, I'm typing the goal here, but then you see the interaction here, right? So you see the goal as well as the interaction. However, all the error reports will come, or output, if you do a write, the write will come in this window to make things more confusing. So let's try to solve example 5, which was supposed to be done in the lecture, but we didn't have time for it, which is a puzzle. The best thing to apply CLP, constraint logic programming, to is solving of puzzles. Last semester I was teaching a module called constraint logic programming, and all we did was puzzles, right? Puzzles over puzzles over puzzles. What I'm showing you is a little bit of the simpler ones. Right, the more complicated one was the lady and the tiger, but in that model we did a lot tougher ones. The interesting aspect here is what we want to focus on is the language, the fact that the language is very expressive. We don't want to focus on programming techniques too much, so the examples are very straightforward. And what I wanted to appreciate is that a language has been created which takes that thing, right, and translates it into something that is obviously correct because the translation is so simple. Going from the English text to the program is so simple that you will never have any doubt that the program is correct. Right? From a software engineering perspective, this is a huge thing because most often what happens is that you spend like 2 weeks writing a piece of program, and then 2 months later when you go and try to add a feature, you look at that program and it's like you see it for the first time. And you spend 2 more weeks to understand what you did 2 months ago so that you can add your feature. If you're asked to look not at your program but at somebody else's program, right? Those 2 weeks become even longer. The original author may have spent 2 weeks to write it. You might spend 1 month to understand what's there, right? So clarity and ability to understand code very easily is great value in large-scale software development. Remember that. Often, if you read software engineering books, most software engineering books will not tell you learn CLP because that's the best. They will try to teach you how to write good C++ or Java programs, right? Because these are the languages that are preferred in practice. They would tell you, for instance, that sometimes you would prefer, or development teams would prefer, solutions that are less efficient but more readable, instead of solutions that are very efficient but not so readable. Exactly for this reason, because the cost of testing and debugging code that is unreadable is very, very high. Many, many hours and many, many thousands or hundreds of thousands of dollars spent in debugging and testing. And if you add up all the milliseconds that you lose by running the less efficient programs, it might not end up to the hours that you have spent in debugging the program, right? If you add all the milliseconds across the entire, all the systems running the same program, less efficient, it might still not add up to, it's not usually hours, it may be months or years of debugging. Some programs become completely doomed because they can't find bugs. It's been many, many cases like that. They brought it to a point where it had bugs that nobody could find them. Yeah, there are some horror stories, and there are quite a few books that. Have you read The Mythical Man Month? I think it's required reading in software engineering. Has Damit told you? Have you taken software engineering? Some of you? Nobody? So Mythical Man Month. I think it's required reading for the software engineering module when you take it.
Now we are reading the reward.
Pardon?
In the 2106, we can choose one is the minimum one, the other one is the reward. More
Modern one, right? Yeah. But nevertheless, so many, many, many horror stories. Like that. So projects in which people they decided that the project was going to take 2 years. So 2 years, it's nowhere near finished. They extended it by more 2 years. They think it's close to completion, but they have bugs to solve. And they say, just a few months. And in just a few months, bugs are still not solved. Then they ask for funding, just a few more months, bugs still not solved. And like after 6 or 7 years, they decided to scrap it. It's been many cases like that. So yeah, anyway, what I'm trying to advocate is that sometimes the language makes a huge difference. It's not just the programming technique; it's the language that makes the difference. And the reason why some programmers prefer, for instance, Python over Java is precisely that. They look at a piece of code and they find it easier to read. Okay, so let's try to solve this one. It's a classic. It's called Who Has the Zebra, right? Who owns the zebra? We have five people living in 5 houses. So it's 5 categories, right? So we have people, houses, pets, drinks, and cars, right? So we have 5 people. Each of them owns a pet, a car, lives in a house of a certain color, and drinks a certain drink. And all are different across the board. Nobody drinks the same drink. Nobody has the same kind of pet. Nobody lives in the same house. So we're given the constraints listed here. And from this, we have to find out all the details. Who lives in what house, has what kind of pet, drinks what kind of drinks, drives what kind of car, right? So these are the constraints. You can read them. I'm going to go through the program because it really makes no difference. You won't be able to solve it in just a few minutes by just looking at the constraints. But right, we have things like Spaniel owns the dog. We have things like the person who drives the Ford lives in the house next to the owner of the Fox. All right, so all constraints are of this form. So the question is, how do we solve it? Of course, we write a CLP program. And we want all these, how many of them are there? 12, 13 constraints to be encoded in a very readable form. But we have to set up to create a certain framework, a certain environment to be able to do that easily. So we're going to have 25 variables, 5 people, 5 houses, or 5 colors of houses, 5 pets, 5 drinks, 5 cars, right? 5 makes of cars. And what you see here is just a means to provide nice output, right? So we don't want to be too concerned with that. But you can see already that the variables that we're going to be using: English, Spaniard, Ukrainian, Norwegian, Japanese. These are names of people. Red, green, ivory, yellow, blue are houses. Tea, milk, orange, coffee, water are drinks. Dogs, snails. Imagine somebody has snails as pets. These people. Dog, snails, fox, horse, zebra. Right, so these are the pets, and these are a mix of cars: BMW, Toyota, Ford, Datsun, and Honda. So you can already see them and group them together because we want to have some sort of a printout. All are grouped in an equality. Equality is just a data structure here. It doesn't mean constraints. We have a list of lists, and this list will be printed out, right? And the variables are going to take up values, so they're going to become numbers. Whereas on the left-hand side, we have atoms. So that will tell us which value each variable has. Because you're going to see, for instance, English equals the value of English. So you're going to see something like English equals 3, which means that the English person lives in the 3rd house. And then you're going to see some color having the value equal to 3, which means that the color of the 3rd house is whatever that color is. Then you would say maybe fox equals 3, and it means that the fox is the pet of the English person. And then you're going to see maybe BMW equals 3, which means that the owner of the 3rd house, which is the English person, drives the BMW, and so on and so forth, right? So in each group of variables, the variables need to be distinct. But across the sets, variables that have the same value pertain to the same house, right? So that's how we think, right? We think of houses 1, 2, 3, 4, 5, and we're trying to find out who lives there, what kind of pet lives there, what car is parked in front, what color it has, what drink is being drank in that house. And that will solve the problem, essentially. So once we have set this up, right, we have to group the people into the 5 groups, right? So we have a group of people, we have a group of colors, group of drinks, group of pets, group of cars, and we're going to put all the 25 variables in one set. So this is what this predicate is going to do, put them all in one set. And we're going to say that all the variables have values between 1 and 5, because all the things pertain to the houses from 1 to 5, right? But then in each group, all the variables are distinct. So all the people are distinct. This is one information that you don't usually see. You have to derive on your own from the puzzle, right? The puzzle doesn't tell you that people are distinct. It's well understood, right, that the English and the Japanese are not the same person. But when you go to the realm of mathematics and you denote by variables different entities, it's not clear they're not the same unless you say so. So as you say, whenever you say person X and person Y, right, it's not clear they're distinct unless you say X not equal Y. So we have to explicitly say that. And also, it's sort of understood from the question that the colors of the houses are distinct, the drinks that are drank in each house are distinct, the pets are distinct, the cars are distinct. So it's important to state all this. And once we have done that, we have set up the environment for encoding the puzzle. So for the rest of the puzzle, we're going to have one line of the puzzle represents one line of the program represents one line of the puzzle, right? So you can see that the English woman lives in the red house is encoded as English equals red. So English being a value means that the English woman lives in the house with that number, and red equals a value means that the house with that number has the color red. So you can immediately say English equals red. The Spaniard owns the dog. So very straightforward. The coffee is drunk in the greenhouse. When I read coffee is green, I'm thinking coffee has color green. And what coffee is that? But coffee is drank in the greenhouse. Ukrainian drinks tea, the next one, right? Green is ivory +1. So the greenhouse is next to the ivory house. And actually, it says it's to the right. It's immediately to the right of the ivory house. So assuming that the houses are neighboring each other because they're placed in consecutive order, right? Greenhouse should be ivory house +1. BMW owner owns snails. No comment there. Yellow house has a Toyota, right? Milk is drank in the third house. Norwegian lives in the first house of to the left. Then neighboring, right? So the driver of the Ford and the owner of the Fox are in neighboring houses. So this is how we say that. The absolute value of the difference is 1. Also, the owner of the Toyota and the owner of the horse are in neighboring houses. Same way, same thing. The owner of the Honda drinks orange juice in this way. Japanese drives the Datsun in this way. Norwegian lives next to the blue house, right? So this is how we say it. And we're done. So all we have to do now is generate combinations and let the system find a solution. So we do a labeling, and that's it. Finished. Right? So let's see this at work. So I'm going to cut and paste into, I could read the file in, but it's just easier to do it this way. So this thing has a compile scratch pad, which doesn't save the file. So you always have to copy and paste. And we can compile all. And now I say main of answer, and I'm going to get, the append all is not predefined. So in SWI prolog, we have this procedure that appends a list of lists, flattens the list of lists, right? So I can say append of, where's my SWI? Do we still have it? So here you can say append 1, 2, and A, B, and L, and we get 1, 2, A, B, right? This doesn't work in Eclipse, so I had to write my own predicate to do exactly the same thing. And that we have to cut and paste. Okay, this worked. We loaded the IC, right? I just ran it in the previous class. I have no idea what happened. So what are we? Oh, we're using the FD, not the IC. Sorry. FD is finite domain. It should not be mixed, of course. Okay, so we get a solution. The solution doesn't look very nice because we haven't done any special formatting. We're going to do that in a minute. But you see, so the English woman lives in the third house, Spanish in the fourth, Ukrainian in the second, Norwegian in the first, Japanese in the fifth. And the solution is obviously unique. Third is green, third is red, fifth is green, fourth is ivory, first is yellow, second is blue, and so on and so forth, right? So we get this unique solution, right? The number represents the house, and each of the atoms that are equated to that number will tell us what happens with that house, who lives in, what pet is in, what color it is, what drink is drank, and so on. So the problem is obviously solved in this way. What we can do to make it a little bit more palatable is to sort all the variables and print them sort of nicely. So I'm going to add this predicate, and this defines a sorting predicate. All right, I don't want to load this again. When I compile. So remember the sort in C? The sort in C takes in its own comparison, right? So you put in a pointer to a comparison function. So the same happens sort of here as well. We're defining a special sorting function. And when I say the list L is supposed to contain structures, right? And what are those structures? Are things of the form atom, that is quoted, equals integer, right? Like 5. So this actually is, in the term writing, is equal. Remember, the equal sign, we're just using it for printing. It's not, doesn't have the inside here at this level is not executed. So we're only using it for printing, and it looks like a structure. It's equal applied to atom and 5, let's say, right? And then we're sorting, this being the structure, we're sorting by the second argument, which is this guy. So if we use this sort answer on a list of atom equals number, then the list is permuted so that all the numbers in the second argument appear sorted. All right, so that's what we're going to get out of it. Now, we have 5 lists. We have a list of 5 lists. We want to sort all the 5 lists. If you remember from Haskell, how would we have done that? We would have written a full program, or we would have taken advantage of some Haskell feature. It's going to be in the exam. Yes, again? Yes, using a map. Very good. So we would use a map, apply the sort, map the sort on each element of the list of lists, right? So this is what we're doing here as well. So the main program, which is what we're going to be running, uses this function called map_list in Prolog, which is the equivalent of map in Haskell. So I'm going to call this predicate. Let's do a compile all. Right. So now the print list prints things on the screen rather than returning them as an answer. So in the lower window, you will see the printout. Okay, and you see that every list appears with this number in increasing order, right? So all numbers appear from 1 to 5. So now it's sort of easier to follow, because if we look at the English, right? The third house occupied by the English has color red. Milk is drank there, owns snails, and drives a BMW. Okay. Now it might be strange that if you read carefully the puzzle, it sort of ends with this twist. It says write a program that finds out who owns the zebra and who drinks water, and you might be surprised because the zebra was not mentioned in the constraints, right? That's because you can derive by elimination who has the zebra, right? Only 4 animals have been mentioned. So you're going to find one house that doesn't have an animal, and by elimination, that's the house that must contain the zebra. And the same with the water, right? By elimination, you'll find a house where the water is being drank. Yeah, so that's about it. Questions? Again, so the really cool feature here is that this thing and this thing, from A to N, there's a 1-to-1 correspondence. We have a language that achieves that. Right? Think of how would you write this in C or in Java or in Python or even in Haskell. Right? Maybe probably, I would guess 100, 150 lines. Okay? Good. Next one. So for the next one, we're going to have an optimization problem. So we're going to push the language a bit further and add the possibility of optimizing some value. So you have to remember your physics. There's a seesaw. Seesaw is actually, you might be surprised, I actually found what a seesaw was in English. Actually, I knew in my native language, which is Romanian, I knew what it was, right? But I found out what the English word seesaw meant when I read this problem, like a few years ago, of course, when I started teaching constraint logic programming. Right, so it's this thing that this board that can swing like this, right? So people sit at the ends, and they try to swing back and forth to create a bit of momentum, so they can swing either to the left or to the right. So here we have the problem. We have 3 girls with some names, L, F, and S. We're going to use the variables L, F, and S in our program. They're on a 10-foot long seesaw, which has a displacement of seats as you see it there, right? Everybody has to sit somewhere, and they want to sit in such a way that they're as close to balance as possible, right? You can't guarantee, because the slots are discrete. It's not a continuous interval on which they can sit. It's discrete places. You cannot guarantee balance, but you can try to be as close to balance as possible. So they will. We have to find the seating, and then what's the law that allows us to compute when balance has been reached, or how close to balance we are? What law of physics do we have to use? If you went into computer science, you don't have to know physics anymore. Yes, moment. What's the moment? The force times the distance times this. No, we said the force already. The force would be the weight times the g times the gravity, but times the sine of the angle between the force and the arm. And if that angle is 90 degrees, which is in this case, then sine is 1, and we can just ignore it, right? So we can just consider the weight, right, mass times gravity, times the arm of the place where the force is being applied, right? Now, obviously, we're going to have an equation, and g can be simplified away, right? Gravity can be simplified away. So we're going to have the simpler case when we're just using their masses, right? Weights, masses, which are measured in stone, which I don't know what it is. I'm just assuming that that it's some unit of weight. Something that we can multiply with. So what we're going to do is multiply the weight times a variable distance, but that distance is an integer, right? Is a whole number of feet, and we want to satisfy this constraint. There's an extra constraint there. They also wish to be able to swing their arms freely, requiring that they are at least 3 feet apart, right? So we will also have to satisfy this constraint. So the question now is, how do we minimize? How do we get as close to balance as possible, right? We have constraints. We have seen how to define constraints previously, so that's going to be the easy part, right? But we want to do the minimization as well. Actually, that turns out to be not very complicated either. So move on to the next question, to the next place. And here I've done quite a bit of extra explanations, so we can. We're going to simply confine ourselves to this one. The rest of the problem would be what I would normally do: go into a generalization where we would try to solve the problem for any length of the seesaw, any number of people with any weights. Right. So. We would be encoding that. But for the time being, let's just focus on the 3 people at hand. So what do? We start with variables. We're going to use, because it's an optimization problem and we want to perform efficient optimization, we're going to use branch and bound as a method, which from in the previous class, nobody has heard of it. Has anyone heard of it here? How much have you heard about it? Do you know what it is, or just like cursorily encountered it? But do you know well what's happening there, or?
It's like the first case break into two or more subtrees. You need to calculate the upper bound or lower bound.
Yeah. So you maintain a current local optimum, and you're trying to not find solutions that are worse than the current optimum, right? That's the optimization. So we're going to try to understand how that works. Let's look at a constraint. So we have 3 variables, and we're specifying that they're between -5 and 5, right? So these are the locations of the 3 people. Also, the 3 people have to be 3 feet apart. So this is how we say that any 2 people have to be at least 3 feet apart, right? Now, do I have to say that they should be all distinct? Because we cannot have 2 people in the same seat. Should we say all distinct? Why not? Yes, so they're already 3 feet apart, so they can't sit on top of each other, right? They would not satisfy the constraint of being 3 feet apart. So that would be redundant. We can add it. That would be redundant. This is the momentum, right? the weights times the lengths. We're going to consider that, we're going to assume that what is on the left-hand side of the seesaw has negative distance. Therefore, we only have to add them. We don't have to think which is on the left, which is on the right. And then, if we use the labeling, we would get all the solutions in integers, meaning all the places where these people can sit, right? Irrespective of whether the seesaw is balanced or not. So what we want to do now is to minimize, right? We're not guaranteed to reach 0. We could say it equals 0. We can ask that, but we might not get a solution in that case, right? So we want to be as close to 0 as possible. So then, this branch and bound library has a procedure called minimize, which applies to labeling. So it takes a generator of solutions, and it minimizes across those solutions the expression that is provided as the second argument, which is essentially the cost, right? So we're thinking of the cost being the balance, the momentum, and we want the momentum to be as close as possible to 0 in absolute value, right? Because a large negative momentum is not good either. So we want the absolute value to be as small as possible. And this should solve it. Right, so I'm going to, well, let's make it, let's say main, so as to make it easy, because we want to load the libraries in one go. I'm actually going to close this first. So some libraries don't mix well with each other. Some do. Some there's no problem. Some don't, and I'm not very sure which is which. So just to save time. Okay, so now running. So it compiled all right. Now running main L. Get a solution. Oh, did I define 2 L's? Answer. Good catch. Type error. Oh. So branch and bound works in real numbers. In general, in constraint logic programming, it is agreed as a convention that all the operators starting with hash operate on integers, whereas those starting with dollar operate on real numbers. You shouldn't think that hash is an operator that makes equal or other operators work on integers. It's just that this is an entire operator, and by convention, those who made the operator names, they put a hash at the beginning of every operator that operates on integers and dollar for reals, right? And obviously, we cannot guarantee this cost to be an integer in general. Yeah, so let's compile again. Branch and bound requires. Did this compile correctly? Yes. All right. So the interesting aspect now is that we see how the system is trying to find a solution. So it will perform the labeling, and it will first find a solution would cost 57. Right? And it will remember that. So it just tries one combination. It just tries and find the solution would cost 57. So that is done by performing. Maybe I have it somewhere, so it stays in the. Okay, so here, right? So we have the 3 variables. Each of them are in this domain, And the labeling will make choices, right? It will create a tree of choices. We'll say, let me choose -5 for L, right? And then let me choose -5 for F. And then it will see that -5 is not 3 feet apart and will fail, right? It will fail before reaching all a complete combination. Then it will try -4 and it will fail again. Then maybe -3, and then maybe -2. -2 is acceptable, so it will continue on, and it will perform choices here. So it will try -5, but it's not going to work. -4, not going to work. -3, not going to work, right? Because it's not 3 feet apart from either of the previous ones. -2, -1, or 0. So 0 should not work. 1. So it finds the solution and computes the cost, right? This is a potential solution. It satisfies all the constraints. It computes the cost, and that's the cost. So now it will backtrack and try to find a different combination, right? But at this very point, when the solution with value 57 is found, right? It will add at this right here. It will say cost less than 57, which means that I'm not interested in. I already have a solution that is 57. Any solution that is cost higher than 57 is not interesting because I'm trying to minimize. So I'm not interested in any solutions like this, right? So I inject this constraint. The branch and bound method injects this constraint into the remainder of the search process. Now, whenever we have this extra information, what happens? The constraint solver propagates this information and hopefully shrinks some domains. This is the essence of progress in constraint programming. Whenever you have a new constraint, right, you make it interact with the other constraints, and hopefully that shrinks the bounds of the other constraints. And at some point, you either get domains that are empty, which means that you have failure. And if you have failure, that's a good thing. You want to have failure as early as possible, because in the search, most often you're going to fail. You're going to fail, and at some point you're going to find a solution. But you're going to fail many times before finding a solution, and you want to fail as early as possible. If you have a combination predetermined that you're going to try, right? Let's say you settle on the combination of, let's say you have 10 variables, and each variable has 10 values in their domain, and you pick one combination across the 10 to the power of 10 combinations. You pick one, and you say, I'm going to try this one. So the question is, in which order would you like to set the values to those variables? And the answer is in the order in which that will allow you to fail quickly. Because if you're going to fail, you're going to fail anyway, right? So you're going to do what? Take one variable, put the value inside. See, have I failed yet? If no, take the second variable, put the value I have chosen for it inside. Propagated constraints. Have I failed yet? No. Move on, right? And keep going till either you have managed to assign all the 10 variables or you have failed. But if you fail, you would have failed, right? You generally don't. Let's say you fail at the 7th variable. You generally fail not because of all the 7 variables being assigned, but because of maybe 3 variables being conflicting with each other. So if you're smart enough, if the constraint solver is smart enough and picks those 3 variables first, it may fail after the 3rd variable instead after the 7th variable. The order in which the variables are going to be picked doesn't change whether the combination is going to make the constraint succeed or fail, because it's a logical formula, right? So we want to fail quickly. So what is hoped is every time we add a constraint like this, propagation will shrink constraints, and right will make the process go faster. We're going to go to the upper level through backtracking, and we're going to have even fewer choices. Okay. So what happens next? We're going to find, because of that constraint being imposed, we're going to find a new optimum. We're not going to find solutions that are lower, that have cost higher than 57. We're only going to find solutions that are lower than 57. And we find a partial solution, a local solution of cost 53, and immediately we impose that constraint. We inject that constraint in the entire search. The propagation of that constraint will shrink some of the domains, right? And because the constraint is there, no solution with cost higher than 53 will be found from this point on. So you see the cost slowly, monotonically decreases, right, until it will reach some value that is the minimum. In this case, actually, perfect balance is attainable, but this not necessarily be the case. So we can change some of the values there. Not here, not here. We can change some of the values and create a situation where 0 is not possible. So let's change 4 to 3, for instance. Oh, we still can. Completely different. Now let's put one that is really large, 20. Small, I think it would be easier. Yeah, you see, so the best cost that we can get here is 1. So it will say, found a solution cost 41, found a solution cost 21, found a solution would cost 1, and found no solution would cost 0, 0, right? So we're operating, actually it operates on integers because the values can only be integers, everything is integers. So when you say less than 1, it means less than equal to 0, so we're trying to find a solution between 0 equal to 0 as the next minimum, but no solution can be found, so the current minimum would be 1. And I'm assuming that if we're going to make this 25, we're going to get something that is even further away from 0. I compiled it, right? So still 1? Very strange. 35. Let's make them obese. Let's make them American. Right, so now the smallest cost is 3. Right, and it says there's no solution, for no solution will cost between 0 and 2. Okay? So that's what branch and bound is. So injecting this constraint of the current optimum, right, optimizes a lot. So if you would be able, we would be able to make statistics into the number of nodes. This is a search tree, right? It's backtracking through a search tree. If you look at the number of nodes that are visited with branch and bound and without branch and bound, you would see that branch and bound optimizes the process a lot. Okay, so this is it. Applications of this. For instance, you can think of creating a timetable. You have a number of classes and a number of students, a set of students. Each of the students has to take a number of classes. You have a number of teachers. Each of the teachers has to teach those classes. You have a number of classrooms, right? Each class has to be scheduled in one of the classrooms at a specific time slot. So you have a set of time slots. And then, so you know, it may be the case. What are the constraints? Each classroom at each time slot has only at most one class, right? Each teacher teaches in any time slot at most one class. Each student in any time slot attends at most one class, right? Each classroom at any point, did I say that? Has only one class scheduled. So once you have these constraints, it's very likely that there will be a multitude of solutions, right? So you can think of imposing an optimization on it, right? So having some cost value that you would like minimize. For instance, you assign an unhappiness value, right, depending on how early the classes are. Classes starting at 9 create more unhappiness, and then you multiply the unhappiness with the number of people attending it, right? So at 9, people are more unhappy. At 10, they get less unhappy, right? 11, they're happy. I don't know, when are you the most unhappy to attend class? And then you want to schedule and minimize the overall unhappiness. You sum the unhappiness of all the people in all the system, and then you try to schedule so that you minimize that. Right? So imagine that a specification of such a system, which would be very difficult to solve in C, C++, whatever, in this kind of language would be relatively easy. There are a few people in the department that do this at a much higher level than me. More specifically, Roland and Martin. They're still doing. The father of CLP, of this kind of paradigm, is still in our department. It's Jackson. Yeah, so when I joined, which is about 15 years ago, the programming languages group was exclusively a constraints programming group. In the meantime, we have like diversified. So I'm not doing constraints programming for research. I'm doing program verification. But Roland and Martin are still active. Martin has even a company that produced a software called FriarTuck, which was used to scale activities on the space shuttle. It's been a few years, but it's been featured in the news. And when actually there's no space shuttle program anymore, right? So that has been phased out. You heard that they drove the space shuttle through Los Angeles. They put it in a museum, and they had to cut trees on the side of the road so that the wings could go in. So the environmentalists were very unhappy that so many trees were cut. So the constraints programming was quite strong. As a research area, it's also been superseded by SMT solving, SAT modular theory solving, right, as a method of solving problems. But SMT solvers and the SMT syntax doesn't meld with the syntax of a programming language so well as it was the case of Prolog and constraints, right? So constraint logic programming is a perfect example of embedding a language into another language and creating a new paradigm, which is extremely powerful and useful, right? So for this reason, it's a good case study, and I would have liked to do a bit more, maybe work a bit on SQL, but I don't think we're going to have the time. So, and I think I've overloaded you already with a lot of stuff, so you know enough for one module. So we're going to stop. We're going to stop here. Okay, so that's about it in my presentation for today. If you have any questions, if you want to stick around and talk some more, feel free to. But otherwise, the lesson is finished.